Okay, so example set 4 on rational expressions, we're asked to continue to look at these expressions and try to find vertical asymptotes. And so vertical asymptotes are going to happen where we saw, like our previous graphs, they're going to look like at a point we're either going to positive infinity or negative infinity. And it can be multiple ways. It can be that on both sides that it's split. It can be to where both of them end up going to positive infinity. Or of course you can have the opposite of each of those as well. So these are all our different vertical asymptotes. You have that. You can have, of course, they can both go to negative. Or you can have where this side goes to negative and that side is coming from positive. So the 4 combinations of positive, negative for the 2 different sides. Now where those things happen is generally where the denominator is going to equal 0 with a little bit of difference in there. So you can put these things in a graphing calculator and find it and see exactly what it looks like. But generally where you want to look is set the denominator equal to 0. So x times x plus 5 equal to 0. And so that means that either x equals 0 or x plus 5 equals 0. So x equals 0 or x is equal to negative 5. And then really the best way is to kind of look at it. And so if we took out a graphing calculator and looked at it, what we would find, or by plugging in points, we would see as we got to negative 5, we would see some asymptotes, whereas when we got to 0, we would see something a little bit different. So I'm going to punch that in my calculator. So if we graph this in our calculator, what we see is that at negative 5, we do in fact have an asymptote. But what happens at 0 does not look like an asymptote. It looks like the function just keeps going. And so what's going on there is a little bit more of a mystery. So what we would notice is since x is in both the numerator and the denominator, that's going to lead the same expression is in both parts. What you actually end up with is a hole there rather than an asymptote. So the vertical asymptote to this is simply x equals negative 5. And we'll talk more about holes as we talk about limits in the upcoming slides. So again, on part B, we want to find the horizontal asymptotes. And so if we graph it, we see that it looks something like this, the expression 15x over 3x squared plus 1. So it looks like as it goes to infinity or negative infinity, it seems to be going to 0. So it looks like the answer would be that y equals 0. Now how could we know that? Well, one of the ways we can know that is what we're talking about here for asymptotes is generally what is happening. We want to know what is happening as x goes to infinity. The same type of questions we asked on the previous problem. F of x goes to what? And as x goes to negative infinity, f of x is going to what? And so one of the ways we can tell that is if the biggest power in the denominator is greater than biggest power in numerator, then y equals 0 is the asymptote. So anytime you see that you've got a bigger power down here, in this case 2, than you have up there, in this case 1, y equals 0 is where that's going to end up going. Because as we go to really big numbers, the bigger the power, the faster it grows. So squared terms are going to grow a lot faster than the 1. By a similar token, those that are cubed are going to grow faster than squared, and so on. So anytime that this power is bigger, we get y equals 0. We continue on with part C. So by graphing, we have, again, we put the function into our calculator. We see it looks like it levels off here and levels off there. So it appears to have a horizontal asymptote, but how do we find it? Well, from the graph, if we looked and traced, it looks like y equals 4. But where does that come from? Well, similar to our previous one, we can look at the powers in the powers of the expressions. So if biggest power in denominator equals biggest power in the numerator, the asymptote is the ratio of the coefficients. So again, we talked about in the previous one, if we had a smaller one, this one grew so fast that it didn't matter what we had up there, it kind of swallowed it up. If they're equal, they're going to grow at the same rate. Square terms grow at the same rate. Anything smaller than that are going to get swallowed up. So just like when we had 15 up here, 15x up here over 3x squared, if we had 15x over 5x squared, it would again get swallowed up because as we go out to infinity, this gets so much bigger than that. So the only ones we have to worry about are the biggest ones. And then, so if they're equal, then in this case, y is 20 over 5, which is equal to 4, which is the same thing we found from our graph. So that's how we would do it if the expressions are equal. Okay, and so part D, we have the third type of example. So in this case, we have the power in the numerator is bigger than the power in the denominator. And so in this case, we see if we graph it, as we go out to it just keeps going. So in this case, there is no horizontal asymptote. So there's not one approach. So that gives us our third rule, which is if biggest power in denominator is less than biggest power in numerator, then there's no asymptote. So there's your four basic ways we work on finding asymptotes. For vertical asymptotes, we're going to check with the denominator is equal to 0, but ignore poles. So whenever the same exact expression is in top and bottom, you end up getting a hole. Where it's not, you get an asymptote. For horizontal asymptotes, again, we're checking behavior as it goes to plus or minus infinity. So if the top power is lower, it goes to 0. If they're the same, we use the ratio of the coefficients. If the top is bigger, then there's not one. And that's how you deal with finding asymptotes.